Okay, so let's say if you have a series in the form, say the sum from n equals 1 to infinity of 1 over n to the power of p, which is just equal to 1 over 1 to the power of p plus 1 over 2 to the power of p plus 1 over 3 to the power of p, all the way to infinity. This is a p series, where p is just a constant. Okay. So the only thing that makes a p series a harmonic series is just making p equal 1. When p is equal to 1, then you have a harmonic series. So it's just a special circumstance of a p series.
Does that mean there's only one harmonic series?
Yep, just when p is equal to 1. But actually, it's more than one because it can be written different ways, and I'll show you in a second. So from n equals 1 to infinity of 1 over n, which is 1 over 1, which you might as well say 1 plus 1/2 plus 1/3, is a harmonic series. Okay, and the reason there's more than one is because most of the time a harmonic, not most of the time, but sometime, it can be written a little bit differently. So a general harmonic series can be written as the sum from n equals 1 to infinity of sum 1 over a times n plus b. So it can be written like that. Thing is, if n gets big enough, the b doesn't really matter. Okay. So what we want to find out is, for what values of p would make a p series convergent or divergent? Okay, and for these we're going to use the integral test. And I'll start on a new sheet since I'm pretty sure this one will fill up pretty quickly. Right. Oh, we're still writing.
It was just saying for what values of p will p series be convergent or divergent?
Both. Yep, convergent or divergent. So we're going to find out which values of p would make it convergent.
Okay.
Okay, so let's say if we want to start, we'll let p be less than 0, or basically a negative number. Okay, so if p is less than 0, then the limit of 1 over n to the p as n approaches infinity actually equals infinity. And proof of that is if p is negative, we'll let p equal some negative k. Okay, so that means you have the limit as n approaches infinity of 1 over n to the negative k. That negative is just brought up top. So that's the limit of n to the k. And as that gets bigger, it's just going to approach infinity. Okay, so second, we're going to let p equal 0. Okay, so that means, well, not really, but we're going to prove it anyway. If p equals 0, then the limit of 1 over n to the p as n approaches infinity is just going to equal the limit, well, not that way, just 1 over n to the 0. I guess you can, yep, into the, I forgot my limit, might as well put it there. No point in skipping over it. Limit of 1 over n to the 0 as n approaches infinity, which is just the limit as n approaches infinity of 1 over 1, which is 1. Okay, so remember, test for divergence is as long as it doesn't equal 0, it diverges. Uh, 1 over n to the 0 equals 1, which is not equal 0. So the series diverges. Okay. So just from those two, we know that when p is less than or equal to 0, it diverges. Okay. So what about p is greater than 0? Okay, so we'll kind of block this off. Okay. So we already know that if p is greater than 0, then f of x equals 1 over x to the p is continuous, positive, and decreasing. Oh, for x is greater than or equal to 1. Okay, so that means by the integral test, if you remember, the integral from 1 to infinity of 1 over x to the power p with respect to x converges for p is greater than 1 and diverges for p is less than or equal to 1. Okay, so there's a quick way to show that it diverges for p is equal to 1. And we can kind of block that off. For p is equal to 1, you actually end up with the integral from 1 to infinity of 1 over x with respect to x, which is equal to the limit as b approaches infinity of natural log of x from 1 to b, which is equal to, uh-oh, forgot my limit. the limit as b approaches infinity of natural log of b. I could put absolute value, but it's approaching infinity, so we don't need it, but minus natural log of 1. Okay. So we know natural log of 1 is 0, so that just